Ready? So, you may have questions from the WebAssign stuff for us to look at. I think so. Yeah, it's not due to Thursday. You're right. Well, we had one. We got the linear stuff that's due tonight, I think, and then the function stuff's due Thursday night, I believe. So we did have, yeah. All right, so I will give you your test back, okay, and let you look at those, but we'll do that last, okay. So, this is not a really long section, so we'll do this and then give you your test back, and then I'll hang around and answer questions if you have questions on any of it. Okay. Okay. So we want to kind of get into some more detail about what the graphs of different functions look like. Okay. That's what we're going to do in section 2.2. We've worked with a few graphs already. We've done some linear stuff, and then we talked about graphs a little bit last time. I'm going to get into more details today. Okay. So first of all, we'll have a little definition here. Okay. So here we're thinking about our function as a collection of points. Okay, so we've got the collection of all points x comma y such that y equals f of x. So that means we're taking the x's, putting those through our function, and then we're calling the values we get out our y values, okay, or our f of x values. Okay. If we take all of those points and plot them all, we get the graph of our function f of x. That's the idea. That's what we mean when we talk about the graph of a function. That's cheating a little bit to say that that's what we're making when we're drawing the graph, because a lot of functions we actually end up with an infinite number of points that satisfy the function relationship. So really we're not plotting all the points, we're kind of connecting the dots between where the points would be. But the idea is if we did take all the points and put them on the graph, then put them in the plane, then we would get the graph of our function. Okay. So let's think about an easy function. Okay. Let's think about a simple little function here. So what's this function telling us it does? It says that we take our input, our x value, and then we add 1 to it, and that's how we get our output value. So nothing fancy there. Okay. If we want to figure out a few values of our function, maybe we would try 3 as our input. And we would get 4 for our output. Okay. That's no big deal there. We're just adding 1. We could do a few more if we want to use 0 as the input. We get 1 as the output. We could do a negative number if we wanted to. Maybe -2 is our input. We get -1 as our output. Okay. Every time we do that, we're finding some pair of coordinates. Okay, we're finding a point that would be on the graph of our function. And because if we go back to our definition, it says all the points x comma y where we take x and use it as our input and figure out what we get as our output for y, those are on the graph of our function. So what we're doing here is we're saying that the point 3 comma 4 is on the graph of our function here, and the point 0 comma 1, that would be on the graph of our function, and the point -2 comma -1, that would be on the graph of our function. So anytime we pick an input value and we get an output value out of our function, we're figuring out a point that's on the graph. And the idea when we draw the graph is we try to look at what the picture would give us if we did that for all the possible values that work with our function. So on that one, it's easy enough. We can go ahead and make a graph for it. We've already dealt with these type a little bit. Let's get some graph paper here for the pull up. Okay. So what do we know? We know 3 points that are on the graph. We've got 3 comma 4. All right, so to the right 3, up 4. We got 0 comma 1, so none left or right, up 1. Another one there. That's actually a special point because that's where our graph crosses the y-axis. You remember what that's called? Y-intercept. Y-intercept, yep. And then we've got the point -2, -1. So to the left 2, down 1. Get that. And if we connect our dots, we don't have my ruler today, so it's a little wiggly, but we get our graph. Okay. And looking at the graph of a function can be really useful because we can get tons of different kinds of information. We know if we, looking at the graph, that if we plug in a bigger x value than any of these that we plugged in, are we going to get a bigger y value or a smaller y value than what we got with these other three? We plug in a bigger x value, something over here, is our y value going to be bigger or smaller than these three? You got to be bigger, right? Because it's going up. Right? So the farther we go to the right, the bigger our y values are going to get. That's one thing we can tell from the graph. The opposite's true going to the left. The smaller x value we plug in, the smaller y value we're going to plug in. That's not true for every function. We can see on this graph is true for this one. Okay. That's one nice thing. Another nice thing that the graph does for us is maybe like we want to know about what we're going to get for y if we plug in like x equals 5. But we don't want to actually do the calculation. Then we can look and say, oh, it's going to be about this place on the graph, and we can get an idea of what the y value will be. Really nice to have the graphs sometimes. Okay. So that one was pretty easy, but that same method works for figuring out at least the general shape of any kind of function. Okay, so even if we have some complicated looking function, we can just pick some input values, see what we get for the output. Know those are going to be points on the graph. And if we do that enough times, we can plot the points and get a pretty good idea of what the graph's going to look like, even if we don't know anything else about the function. It's a good way to approach this. Let's think about another function. Oh, well, we can generalize this a little bit. Okay. Since we've already talked about these. anytime we have a function that looks like this, we got something times x plus or minus some other number. What's our picture going to look like? What general shape is our graph going to have? Here's one. It's going to be a straight line. It's going to be a straight line. So if you see that kind of form, you know the graph should come out to be some kind of straight line. So it is nice to have some basic functions in mind and have an idea of what the graphs are going to look like. That way you don't have to plot so many points when you start trying to figure out exactly the graph. Like on that one ahead of time, if I'd have thought about it was a line ahead of time, I could have just done these two and that would have been enough to get my graph. Okay. So if you connect two dots, you get a straight line. Let's think about another function. Here's another one. This time we take whatever input value we pick and we square it. So we multiply it by itself. So maybe you probably already know what this one looks like. It's okay. Let's investigate. So pick a few input values and see what happens. So I'm going to pick some on the negative side, some on the positive side. Okay. There's our function. So whatever number we're inputting, we're going to square it. So we'll have negative 2 squared, or negative 2 times negative 2. So that one's going to give me 4. That means on my graph, I'm going to have the point negative 2, 4. Input, comma, output. Try negative 1. Negative 1 squared will give us positive 1. So I've got the point negative 1, 1 on my graph. Zero is an easy one to do. 0 squared, which is 0. It's okay if we get the same number. All right, because that means my input is 0, my output is 0. It's all right. That's a special point. That's the origin, but it's okay for that to be on our graph. What about if we try 1? We get 1 again as our output. That's okay. If you're thinking hard enough, you might think that might make it not a function. But this is okay because every input we're using is going to exactly one output. That's our rule, so this is still a function. And then if we do 2, we get 4, so 2 comma 4s on our graph. There's 5 points. Let's see if we can tell what our picture is going to look like. Again, a lot of you probably already know. Let's see, we had the point negative 2, 4. Had the point negative 1, 1. Had the point 0, 0. Point 1, 1. And the point 2, 4. There. If we connect those dots, what kind of shape are we going to get? Yeah, we're going to get like a U shape. Okay, parabola is what we call it. And so we'll end up getting this kind of shape. Okay. And in general, it's good to know. See, if you knew that ahead of time, you could feel more confident drawing that in. Okay. If you have no idea what the shape's going to be, then maybe you would want to do some more points, because how do we know it doesn't like dip down over here or do like a roller coaster or something like that? But if you can remember the general shape, then you can just plot a few points and be pretty confident. Okay, but in general, when we have a function like this, or we have x raised to some power, if that power is even, okay, then in general our graph's gonna look pretty much like the one we just did, where we have like a parabola type shape. And it's possible it could go down, but one of those. So let's look at some graphs and we'll see what happens when we change the exponent. The general shape stays the same, but it does change a little bit. There's our x squared graph. Now let me flip this to see a little better. Okay. That's the one we just made. Okay. But we said we should get that general shape as long as the power is even. Now let's look at like x to the fourth. That's the orange one. It's still basically that shape. It's a little bit flatter around 0. Let's do something bigger and see what happens. So we want even though, so like x to the 40th. Okay. What's happening there? As we increase the size of the exponent, the bottom here is just kind of spreading out, and it gets kind of more, takes more of a rectangular shape. Okay. We don't actually get 90 degrees on there, okay, but it gets close to that. Okay. But in general, they're all going to have like that U shape. And then we'll talk about this more next time, but what happens if we have one that opens upside down? We'll have a minus sign out in front, and that would make it go down. You can know anytime you have an x raised to some even power, you're going to have a U shape, and it either goes up or down. Okay. What if we have the other situation? What if we have x raised to an odd power? What's that going to change? Let's figure out some points on the graph, and then we'll try it. So. Let's see, so -2, if we do -2 to the third power, that means -2 times -2 times -2. So -2 times -2 would be +4 times -2 would give us -8. Do the same thing with -1. -1 times -1 times -1 is going to give us -1. Zero's easy. 0 times itself 3 times is just 0. 1, we'll have 1 times 1 times 1, so that's 1. 2, we'll have 2 times 2 is 4, times 2 is 8. So some points on our graph, we've got -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. So let's plot those. Take a look. Some of you may know this one too, but probably less of you than the other one. So let's take a look. I don't know if my graph paper is this big or not. I might have to make do. Okay, so we said -2, -8. So -2, 1, 2, 3, 4, 5, 6, 7. So that would be like down here somewhere. -1, we'll have -1. 0, 0's on there. For 1, we had 1. And for 2, we had 8. So what's the shape look like? It looks something like this. It goes down on the left side, up on the right side. It's just like the parabola, except with the parabola, this part is up here. When we have an odd exponent, it gets flipped down this way. And that same general shape happens any time we're raising x to a odd power. And so then we get this shape. So let's look at a few and see what happens when we make the exponent bigger than that. Okay, so x to the, well, x third power, there's the one we just drew. If we do x to the fifth, still pretty close, right? Still basically that same shape. A little bit flatter. That's kind of the same thing that happened with the parabola. Let's try a big one. So x to the 55, that's odd. That's the white one. So same kind of things happening. Okay. It's kind of flattening out down here around 0, and then we have a steep turn when we get close to 1. But they all have the same basic shape, right? They all go down to the left, and then come up through 0 somehow, and then go up to the right. That happens when our exponent's odd. Okay. All right, look at a couple more. Let's think about this one. This one may be less familiar to some of you. Think about square root of x. So, first of all, what about if we try like -2? Then we'll have square root of -2. What happens with that? If we take the square root of a negative number, we would get a complex number, right? We would get I. So with the functions that we're dealing with in here, we're not going to deal with complex numbers. So on that one, we would say like no real solution. So what's that going to mean on our graph? It means if we go over to an x of -2 on our graph, we're not going to have a point there. We're not going to have a y value that corresponds to that x value. -1, same thing. We're not going to have a part of our graph over x value of -1. So the first place, if we're going from the left, the first place we could actually get a point out of this thing would be at 0. The square root of 0 is 0. 0 zeros on our graph. We try 1. Square root of 1 is just 1. 1's on there. 2 we could find. But if we do square root of 2, we get 1.414, something that's a decimal. So let's skip up to our next number where we can get a whole number. Do square root of 4, we'll get 2. 4, 2. There's 3 points. Let's try that. Let's plot those and see if we can tell what's happening. We said we had 0, 0. Oh, I need a different color. We had 0, 0. We had 1, 1. And then we skipped to 4 and said we had 4, 2 on there. Okay. And then we also said we're not going to have any graph over here. Because anytime we try a negative value, we're not going to be able to get an output. So this one ends up looking something like this. It starts at 0 and then kind of goes that way. We really need a bigger graph to get a real nice picture. So let's look at the good graph of it. So if we do square root of x, and a little bit better picture. So starts here at 0, 0, goes through 1, 1, then it kind of flattens out. We'll go to the right. And again, we don't have any graph on the left side in quadrant 2 and quadrant 3, because over there with the negative x values, we can't get an output out of our function. What we would say there is that the negative x values are not in the domain of our function. Okay. And again, we can kind of generalize this. So that same idea is going to be true. We're going to have about the same shape for any function that looks like the nth root of x when the index is even. We're going to have a graph that looks something like that. So this one's square root, so the index is 2, even though we don't write it down. So going back to our graph, let's do another one here. Let's see. So like 4th root of x. real similar picture, it's flatter. I hate that it picked another shade of blue there. Let's do another one. Let's do like 40th root. Same kind of shape. It goes up and to the right, but it just gets really flat. It's not completely horizontal. It just looks like it because it's really close. Okay. You can tell it's not exactly horizontal, right? It goes up a little bit. It just goes up really slowly. And so that's if our index is even. What if it's odd? I won't make you plot points for all these. Let's just think through them. So I'll do a few real quick. Now let's think about the negative situation here. That's okay if our index is odd. Cube root of -1 is -1. So that's okay. Cube root of 0, 0. Cube root of 8 give us 2. Okay. So let's just look at what this one looks like. Okay, we won't go through all of them. Okay. So the basic shape. And if we have the cube root of x, our basic shape there. So it looks, the right side looks basically just like square root. But with the odd index, we also have graph down in quadrant 3. Because negative numbers are okay with odd index. Something else to think about is this thing is like when we had x cubed, right? It looked like that. So this thing is just like turned around. Okay. X cubed. Okay. All right, one more big one for us to kind of have in our head. That's the last one. The last one. What about this one? We haven't dealt with it yet in here. What does that one tell us to do? Absolute value. Yeah, good. So absolute value says, well, whatever the number is, we take the positive version of it. So absolute value of -3 is 3. Absolute value of -2, 2. We'll skip, we'll go to 0. Absolute value of 0 is 0. 0 is not positive or negative, so that one's slightly controversial, but it's defined as 0. Absolute value of 1. If we have a positive number inside the absolute value, it just stays positive. Absolute value of 2 is just 2. What's this one look like? We plot this thing. Okay. So let's see, we had -3, 3, -2, -2, said 0, 0, 1, 1, 2, 2. If we did -1, we would have got +1. If we did +3, we would get +3. What's it looking like? A V. Yeah, we get a V shape. So absolute value would look like this and like that. Okay. So what's happening with absolute value is it would be a straight line. Okay, so it would keep going down here into the negatives. But the absolute value says anytime we would get a negative answer, we make it positive. So instead of our points being down here, they're up here. So we get this V shape. Okay. That's another good one, another basic shape on. Okay. So what we had? We had straight lines. They're like mx plus b, the straight line. You have x raised to an even power. That's like a U shape, like a parabola. You have x raised to an odd power. It goes down on the left, up on the right. If you have an even root, it starts at 0, it goes up and to the right, but it's really flat. If you have an odd index root, then you have some in a quadrant 3, and then it looks like the square root. And then you have absolute value, you get the V shape. Those are going to be our important graphs right now. We'll add a couple more later, not many more. But you kind of want to know the basic shape for those. Let's see. Good progress, good progress. We don't have much more. Next big topic in this section, we want to think about if we have some graph, how can we tell if it belongs to a function or not? Because we have that rule that says a function sends each input to exactly one output. So how could we tell if it takes an input and sends it 2 different places? Graphically, that's not difficult. We have an easy little test we can check called the vertical line test. So one way to word this is that any vertical line, so we're thinking about drawing in any vertical line we want to, okay? So any vertical line touches the graph or crosses the graph. Intersects is probably a better term. Okay. It says if we have a graph, we're thinking about drawing in any vertical line we want to, that we should not be able to draw in a vertical line that touches our graph more than once if it's a function. Because if it's a function, any vertical line that we draw in is going to touch our graph at most once. Okay. It's okay if you can draw in a vertical line that doesn't touch the graph. It would still pass the vertical line test. But if there's anywhere that you can draw a vertical line where it touches the graph more than once, then that graph does not represent a function. And we would say it fails the vertical line test. So let's think about that. A lot of times people remember this, like if you learned it in high school, it's something that sticks with you. But it's not hard. Okay, so let's see. Here's a graph. Okay. Would this thing be a function? Okay. Looking at it, I say yes. I say no matter where we draw in a vertical line, if I draw in a vertical line there, or there, or there, or there, anywhere, it's going to touch our graph at most once. Nowhere I can draw one in where it touches it more than once. So this one I would say is a function. And what about that one? No, that one's not going to be a function because we've got a lot of places where we could draw in a vertical line and it would touch the graph more than once. And so this is not a function. Not a function. If we have something like this, so like a parabola, but it's sideways, how about that one? That one's not a function. If we draw in a vertical line right there, touches it more than once, that one's not a function. Okay. What about our V shape? That one a function? That one is a function, no matter where we draw in a vertical line. And even if we draw it in right at the point, any of those they only touch once, so this one is a function. Okay. So vertical line test gives us a quick way to just look at a graph pretty quickly. Okay. If we can find anywhere where we can draw a vertical line where it touches it more than once, it's not a function. Okay. If every vertical line that we could draw in touches our graph once or no times, then it is a function. Okay. So what would it be like if you had a vertical line where it wouldn't touch it somewhere? So maybe like because if we drew in a vertical line right here, it would not touch the graph. We've got a gap. That's okay. That's okay. If we draw one in there, still touches once, or over here, still touches once, so this one would be a function. Okay. Questions with the vertical line test? It's not too bad. One last little topic here. And that is thinking about the graph of a piecewise function. So let's look at one of those. So the only difference, they look way scarier, but they're not way scarier. The only difference is that we switch up which rule we're using depending on our x values. Right? So this one says if our x values are positive, our y values are going to be 1. If our x values are less than or equal to 0, our y values are going to be -1. Okay. So if you really need to, you could try to plot some points. Right? Like we wanted to know f of 2. 2 is bigger than 0. So what's our y value going to be? Somebody. Be 1. So we got the point 2 1s on the graph. Okay. We wanted to try f of -1. -1 would be less than or equal to 0, so our y value would be -1. So we'll have the point -1, -1 on our graph. The one that's can be a little bit tricky here, what if we want f of 0, which one matches up with 0, top or bottom? The bottom, yeah, because it's got the or equal to bar for 0. So f of 0, we would use the bottom, so our y value would be -1. So we would have the point 0, -1 on our graph. So if we go to draw this thing, let's see how that looks. Okay. Sorry, it's over here. If we go to draw this thing, let's say we've got 2, 1. We got -1, -1. Well, sorry, I got 2, 1. And then I got 0, -1. Going to be on our graph. So here where we make the switch, okay, any negative number we plug in, we're going to get 1. So we'll have -3, -1, -1. -4, -1, -5, -1, -6, -1. So that part of our graph is just going to look like this. Any positive x value we use, it says our y value is 1, so we're going to have all these points up here. The only thing that's a little bit tricky is that for all the positive x's, we're going to have a y value of 1. But when we get to 0, we have to think about it. The point 0, 1 is not going to be on our graph because we said at 0 we get -1. So we'll have an open circle there, and then everything else will have graph there. So not my best drawing, but we'll have this and this. Okay. Closed circle at the bottom, open circle at the top. Okay. Ugly. Okay. So on each little branch, okay, you can still plot points just like we did on the others. The only place you have to be really careful is where they overlap, like this one, they overlap at 0. You just have to look. The one with the equal bar is going to be where you have a closed circle, and then the one without the equal bar, you'll have an open circle there. Okay. So maybe we'll do another one or two of those to start with next time. Okay. All right, so that's the stuff for that section. So I'm going to stop the video and then I'll